तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we looked at the simplex algorithm and solved two examples, both were maximization problems. In today's lecture, we continue our discussion on the simplex algorithm by looking at the various stages that we go through in simplex. For example, there are three important stages in the simplex algorithm. They are called initialization, iteration and termination. Now, under initialization, the algorithm starts with a basic feasible solution. The right hand side values are always non-negative. So, when we start solving a problem using the simplex algorithm, first thing we need to do is to have the right hand side values non-negative, and then as we construct the first simplex table, we have to make sure that the first simplex table has a basic feasible solution. The algorithm goes through some intermediate iterations, which is called iteration, and then the algorithm terminates when there is no entering variable, and it provides the optimal solution, which is called termination aspect of the algorithm. Now, what are the other things that we need to look at? Are there other issues that have to be explicitly considered, or have we addressed all these issues in the two examples that we have seen? We have not addressed all of them, and we will be addressing each one of them in detail. Do all linear programming problems have optimal solutions? Can we have a linear programming problem that does not have an optimal solution at all? So, we will be looking at that. Does the simplex algorithm always terminate by providing the optimal solution? Can it terminate otherwise? We will have to look at those aspects. Now, let us look at all these three aspects, initialization, iteration and termination, through different examples in detail. Now, let us consider a different type of a problem. We now consider a problem with a minimization objective. So, the problem is to minimize z equal to 3x1 plus 4x2 subject to 2x1 plus 3x2 greater than or equal to 8, 5x1 plus 2x2 greater than or equal to 12, x1 x2 greater than or equal to 0. Now, this is also a linear programming problem, but this is different from the two examples that we have considered. Both the examples had a maximization objective. More importantly, both the examples that we considered had constraints that were of the less than or equal to type. Now, we are looking at a problem which has constraints of the greater than or equal to type. Now, as we did in the previous example, we will convert these inequalities to equations. So, this will become 2x1 plus 3x2 minus x3 equal to 8, and 5x1 plus 2x2 minus x4 equal to 12, x1 x2 x3 x4 greater than or equal to 0. Now, let us explain this. Now, 2x1 plus 3x2 can be exactly equal to 8 or greater than 8. So, we now add a variable x3 which has a negative sign. So, when 2x1 plus 3x2 becomes greater than 8, then x3 will take a positive value, and then this inequality will become an equation. Similarly, x4 is introduced with a negative sign to take care of the fact that when phi x1 plus 2 x2 exceeds 12, x4 takes a strictly positive value. x4 will not take a negative value because phi x1 plus 2 x2 cannot be less than 12. Now we have introduced two more variables x3 and x4 into the problem. Now these are also slack variables like those introduced in the earlier two examples. The only difference here is these are called negative slack variables or surplus variables. The fact that we have introduced negative slack variables to convert a greater than or equal to inequality into an equation also makes these negative slack variables greater than or equal to 0, in addition to the explicit condition that the decision variables should be non-negative. So we stick to the fact that all variables in the simplex algorithm will have to be strictly non-negative, whether they are decision variables x1 x2 or slack variables x3 x4, negative slack in this case. Now we have converted this two inequalities to equations. Now we have to find out what is the contribution of these slack variables to the objective function. As discussed in the earlier example, these slack variables do not contribute anything to the objective function. So the problem now becomes minimize z equal to 3x1 4x2 plus 0x3 plus 0x4 subject to these two and the condition that x1 x2 x3 x4 are greater than or equal to 0. Now let us try to set up the first simplex table. Now what we do here is we set up the table with x1 x2 x3 x4 and we write this is a minimization. So we write 2x1 plus 3x2 minus x3 plus x4 8 5x1 plus 2x2 0 minus 1 12. The objective function coefficient is a minimization problem. Since we are used to solving a maximization problem, we convert this minimization objective to a maximization objective and the problem would become maximize minus 3x1 minus 4x2 plus 0x3 or minus 0x3 minus 0x4. So we would get here minus 3 minus 4 0 and 0. Normally we would have liked to start with x3 and x4 as basic variables as we did in the two previous examples. Now let us see whether we can actually do that. Now if we fix x1 x2 as non-basic and fix x3 x4 as basic as we did in the earlier two examples, then we have a solution x1 equal to 0, x2 equal to 0, x3 equal to minus 8, x4 equal to minus 12, which is not a basic feasible solution. So in all problems that involve greater than or equal to type constraints, slack variables automatically do not qualify to be the initial basic variables because they end up giving an infeasible solution. So we cannot start the simplex table with x3 and x4 as we did in the earlier case. So we should not be doing this. Now we need to do something else. Now what we need to do is to somehow try and identify a basic feasible solution out of this. Once again, this as a system has 4 variables and 2 equations. If we go back to the algebraic idea, then we can evaluate 6 basic solutions for this, out of which 1 or more may be basic feasible. The only thing we have to do is we need to go back and individually evaluate all the 6, which we do not want to do because we have already moved from the algebraic method to the simplex, realizing that the simplex method is better than the algebraic simply because it has better features. So we do not want to go back to the algebraic method and then try to get a basic feasible solution. So what we do now is something different. So the two equations are written again as 2x1 plus 3x2 minus x3 equal to 8, 5x1 plus 2x2 minus x4. So these are the first two equations. Now by merely looking at these equations, we are not able to get a basic feasible solution as we did in the two previous examples. So in order to get a first simple basic feasible solution, we add two more variables to this set. We call them, for example, plus a1 equal to 8 plus a2 equal to 12. If we simply add these two variables a1 and a2 into these equations, and if we rewrite the equations in this form, then we can, now we have 6 variables and 2 equations. So 2 of these will be basic and the remaining 4 will be non-basic. Now we can keep a1 and a2 as basic, treat x1, x2, x3, x4 as non-basic, and then start with a basic feasible solution with a1 equal to 8 and a2 equal to 12. So we add these two variables with a very specific objective of identifying a basic feasible solution. To get a basic feasible solution, we add these two variables. So these two variables that are added are called artificial variables. Most important thing about these artificial variables are they are not part of the problem. For example, x1 could represent the amount or quantity of some product that is made. x3 could represent the amount of a certain resource that is not utilized. So like that we won't be able to have a clear definition of a1 and a2, or a1 and a2 do not have any physical significance with respect to the problem simply because they are not part of the problem. They have been introduced with a very specific objective of getting a basic feasible solution. That is why they are called artificial variables, because they do not belong to the problem. And to clearly separate them and identify them, we use a notation a1, a2 to represent these artificial variables. Now what are the other things we need to do? Now do these artificial variables have a contribution to the objective function? Number 1. Now the objective function is now minimize or maximize minus 3x1 minus 4x2 plus 0x3 plus 0x4. Now we need to find out whether these artificial variables have any contribution in the objective function. To do that, let us go back and look at this problem and this problem again. Now this problem we want to actually solve this problem, but we have ended up creating a new set of equations with two additional variables that we have introduced into the problem, which the problem does not have. So if this problem has to adequately represent this problem, then we have to ensure that these two variables will not appear in the final solution, because if they appear in the final solution, then it means that this problem has not adequately represented this problem. Remember that we wanted to solve this, and then we converted this set of inequalities to equations by adding a negative slack variable, and then for the purpose of getting a basic feasible solution, we have added two more variables into this problem, which are the artificial variables. So since these variables are not part of the problem, they should not be part of the solution. So we have to ensure, or we have to make sure that these artificial variables are not part of the solution and they will not appear in the optimal solution if one such optimal solution exists. And how do we do that? Now what we do here is, for a maximization problem, we give a very small contribution to the objective function. So we write, for example, minus ma1 minus A2, where this m is called big M, this m is large, positive and tends to infinity. Which means minus m is a very small number, and the contribution of these artificial variable to the objective function is a very small contribution. So why are we doing this? We are doing this because now what simplex would do is, out of these 6 variables that we have, it is going to identify that basis which optimizes the objective function. So what we want to make sure is, we also want to make sure that these artificial variables do not appear in the solution. So they should not be in the solution. So now if there is a feasible solution which does not have these artificial variables, and if there is another feasible solution which has these artificial variables, then we have to make sure that the feasible solution that does not have these artificial variables has a higher value of the objective function than every feasible solution that has one or more of these artificial variables, because we are solving a maximization problem. Now because the contribution of these artificial variables is very small, so when if A1 or A2 appears in a basic feasible solution, then because of these minus m being close to minus infinity, the value of the objective function will be very less, and it will be minus infinity. For every basic feasible solution which does not have either A1 or A2, the contribution will be a number which will be far higher than minus infinity. So indirectly what we try to do is, we prevent these A1 and A2 from coming into the solution by making sure that for every basic feasible solution that has A1 or A2, if there is a basic feasible solution that does not have any of the artificial variable, then that solution will have a higher value of the objective function. And since we are maximizing, we have converted the minimization problem into a maximization problem. Since we are maximizing, if there is even one basic feasible solution that does not have these artificial variables, then that solution will dominate every basic feasible solution that has at least one artificial variable. Therefore, if the problem has a solution that does not have A1 and A2, or alternately if this problem has an optimal solution, then obviously that will not have A1 and A2. Therefore, if this problem has a basic feasible solution without A1 and A2, then that basic feasible solution will be better than every basic feasible solution with A1 and A2. Therefore, we are now convinced that by putting this minus ma1 and minus ma2 here, we are preventing this a1 and a2 from appearing in the solution. So now we go back and construct the simplex table. We add these a1 and a2 here. So we have plus a1, 1 0, 0 1, the right hand side values are 8 and 12. Now a1 and a2, the artificial variables are the starting basic variables. Their contribution to the objective function will be minus m for a maximization problem. So we maximize. So we have a minus m here and a minus m here. Now we write our Cj minus Zj. Please remember that we will use this m very judiciously, and you will see how we use this m. We say this m is large, positive and tends to infinity. You will see how we use this. Why we do not put an infinity but we put an m will be apparent once we start computing the Cj minus Zj's. Now let us keep this as minus m. So Cj minus Zj, this is minus m into 2 plus minus m into 5, which is minus 7m. So this is minus 3 minus minus 7m, which is 7m minus 3. This is minus 3m, minus 2m is minus 5m, minus 4 minus 5m is plus 5m minus 4. This is plus m 0, so you get a minus m here. This is 0 plus m, so you get a minus m here. This is minus m minus m is 0, 0. In any case, a1 and a2 being the basic variables will have a 0 in Cj minus Zj. In this example, we do not compute this. For example, we do not put a minus 20m here. Normally we would have put minus m into 8 plus minus m into 12, which will be minus 20m. We do not put any number there simply because we still have artificial variables appearing in the basis. So this number does not convey anything to us, so we just leave it as it is. Now we want to enter the variable which has the largest positive Cj minus Zj. So 7m minus 3, 5m minus 4. Now when m large positive, not exactly infinity but close to infinity, 7m minus 3 will be bigger than 5m minus 4. So we enter variable x1. So precisely for this reason we keep it as big M and we do not make it explicitly as equal to infinity. Now we realize that 7m minus 3 will be bigger than 5m minus 4, so variable x1 will enter. Now to find out the leaving variable, we compute a theta. So this is the entering column, so 8 divided by 2 is 4, 12 divided by 5 is 12 by 5. The minimum value is 12 by 5. So variable a2 leaves the basis, variable x1 enters, and this is the pivot element. So we now have the next iteration with x1 or with a1 and x1 coming here. As usual we do the row operations. So the pivot row is rewritten first by dividing every element of the pivot row by the pivot element, in this case dividing it by 5. So you get 1, 2 by 5, 0, minus 1 by 5, 0, 1 by 5, 12 by 5. Incidentally these values are minus m and minus 3, sorry. This is the pivot row. So divide every element of the pivot row by the pivot element to get 1, 2 by 5, 0, minus 1 by 5, 0, 1 by 5, 12 by 5. Now we need a 1 0 and a 0 1, we need to get a 0 here. So this minus 2 times this row will give us 0. So 2 minus 2 times 1 is 0. 3 minus 2 into 2 by 5 is 3 minus 4 by 5, which is 11 by 5. Minus 1 minus 2 into 0 is minus 1. 0 minus 2 into minus 1 by 5 is plus 2 by 5. 1 minus 2 into 0 is 1. 0 minus 2 into 1 by 5 is minus 2 by 5. And 8 minus 2 into 12 by 5, 8 minus 24 by 5 is 16 by 5. Now again we compute Cj minus Zj. a1 and x1 being basic variables will have 0. Now this is minus 11m by 5 minus 6 by 5. So this is minus 4 plus 11m by 5 plus 6 by 5. So 11m by 5 plus 6 by 5 minus 4 is minus 14 by 5. This is plus m, so 0 will give us a minus m. This is minus 2m by 5 plus 3 by 5. So 0 minus 2m by 5 is plus 2m by 5 minus 3 by 5. This will be plus 2m by 5 minus 3 by 5. So, minus m minus 2m by 5 is minus 7m by 5 plus 3 by 5, and again we do not write anything here because we have an artificial variable lying in the basis. Now, we enter the variable which has the most largest positive Cj minus Zj. 11m by 5 is bigger than 2m by 5 minus this. So, variable x2 will enter. For example, since m is very large, the other constant term, whether it is positive or negative, does not have any impact. So, you only look at the terms that involve m. So, we look at 11m by 5 here and 2m by 5 here. So, variable x2 enters the basis. Now, to find out the leaving variable, we have to compute theta. So, this is 16 by 5 divided by 11 by 5, which is 16 by 11. 12 by 5 divided by 2 by 5, which is 6. 16 by 11 is smaller, so this variable leaves. This is the pivot element. So, now variable x2 replaces variable a1. So, we have x2 here, we have x1 here. And the coefficients are minus 4 and minus 3. Divide, this is the pivot row, this is the pivot element. So, divide every element of the pivot row by the pivot element. In this case, divide by 11 by 5 or multiply by 5 by 11. So, 0, 1, minus 5 by 11, 2 by 11, 5 by 11, minus 2 by 11, 16 by 11. And then x2 and x1 are the basic variables. So, we need a 1 0 0 1, we need to get a 0 here. So, this row minus 2 by 5 times this will give a 0. So, do the row operation for every element. 1 minus 2 by 5 into 0 is 1, 2 by 5 minus 2 by 5 into 1 is 0, 0 minus 2 by 5 into minus 5 by 11 is plus 2 by 11, minus 1 by 5 minus 2 by 5 into 2 by 11. So, minus 1 by 5 minus 4 by 55 would give us minus 15 by 55, which is minus 3 by 11. 0 minus 2 by 5 into 5 by 11 would give minus 2 by 11. 1 by 5 minus 2 by 5 into minus 2 by 11 is 1 by 5 plus 4 by 55, which is 15 by 55, which is 3 by 11. 12 by 5 minus 2 by 5 into 16 by 11. So, 2 by 5 into 16 by 11 is 32 by 55. This is 12 11s are 132 minus 32. So, you get 100 by 55, which is 20 by 11. Now, Cj minus Zj values are x1 and x2 are the basic variables. So, you get 0 here. Now, this is minus 4 into minus 5 by 11 is 20 by 11, 20 by 11 minus 6 by 11 is 14 by 11, 0 minus 14 by 11 is minus 14 by 11, minus 8 by 11 plus 9 by 11 is 1 by 11, 0 minus 1 by 11 is minus 1 by 11. This is minus 20 by 11 plus 6 by 11 is minus 14 by 11. So, this is minus m plus 14 by 11. This is 8 by 11 minus 9 by 11 is minus 1 by 11. So, minus m plus 1 by 11. 16 into 4 is 64 plus 20 into 3 60 124, so minus 124 by 11. Now we look at the Cj minus Zj's and we realize that all these are negative, because even though these are positive numbers, we have a minus m being very large and positive, so both these terms are negative. The algorithm terminates. We have reached the optimal solution with x1 equal to 20 by 11, x2 equal to 16 by 11, z equal to minus 124 by 11 for the maximization problem that we have solved, and we had earlier multiplied this objective with a minus 1 to convert it to a maximization. So in order to get the objective function for the original problem, we need to multiply this again with a minus 1. So the optimal solution is x1 equal to 20 by 11, x2 equal to 16 by 11, z for the original problem will be 124 by 11. So this algorithm terminates this way. Now what are the other issues? For example, a1 and a2 being artificial variables, we do not want them in the basis. That is how we have defined them, we do not want them in the basis. So we actually need not explicitly compute these numbers, and these numbers will always be negative, they will never be positive. Artificial variable will never try to enter the basis at all. So we need not have actually calculated these two numbers, these two which were obvious and these two numbers. But then for the sake of completion we have done all this, and this is how we solve a minimization problem. The moment we have all Cj minus Zj's negative, the termination condition that we know, the algorithm will stop. In this case we have the optimal solution with two decision variables x1 and x2 coming into the solution. Now we have also seen that by introducing these artificial variables, and more importantly by giving this minus m here, we have prevented them from appearing in the optimal solution. Now let us go back to this, we show the same thing in this table. So a simplex table show a negative value because we have solved a maximization problem. So we need to multiply the objective function again with a minus 1 to get the plus 124 by 11 that we have here. Next. Now what are the other observations that we have? One is, it is easier to introduce artificial variables when the problem does not have a visible initial basic feasible solution as we had here. Now this problem does not have a very clear basic feasible solution here, because the basic feasible solution by fixing x1 x2 to 0 would give us x3 equal to minus 8, x4 equal to minus 12. So this is not a basic feasible solution. We might ask ourselves another question: what would have happened if we had defined these x3 and x4 with a plus sign and then force them here to less than or equal to 0? Mathematically it is correct. We do not do that because we are very keen about the fact that all the variables should be greater than or equal to 0. This is actually going to get reflected in the minimum theta rule or the entering rule. So if we have some variables greater than or equal to 0 and some less than or equal to 0, then we cannot blindly as well as uniformly implement the minimum theta rule. So we are extremely concerned about the fact that the simplex algorithm should not end up evaluating any infeasible solution in the middle iterations. We do not want that to happen, and that is ensured by the minimum theta rule, and we would like to keep the minimum theta rule intact and not disturb it. Therefore we would rather introduce x3 and x4 in such a way that x3 and x4 are always greater than or equal to 0, even though they end up having a negative term here. Now that we have learned to use artificial variables to get the initial basic feasible solution, it becomes easy now to solve problems with greater than or equal to. Assuming that right hand side values are non-negative, any greater than or equal to constraint will only give us a negative slack. A negative slack will not qualify to be a starting basic feasible solution. So when it does not qualify to be a starting basic feasible solution, we will have to introduce an artificial variable. Now since we have 2 artificial variables in this problem, we need a minimum of 2 iterations in this example. It turned out that after these 2 iterations, the third one gave the solution. For such small problems, usually the moment all the artificial variables leave the basis, we will get the optimal solution. And as we had indicated, we need not explicitly evaluate these Cj minus Zj values, they will anyway turn out to be negative. Okay. Now let us look at another way to solve minimization problems. Now what we did here is we introduced artificial variables straight away, and then we made sure that they do not appear in the solution by giving them a large negative value for a maximization problem. Now this method that we have used is called the big M method. It's called the big M method, where we have introduced the big M. We also have a very similar method called the two-phase method, which we will see now to handle problems of this type. Now let us work out the two-phase method with the same example to understand what Now what we are going to do in the two-phase method is, we are going to solve the problem in 2 phases. In the first phase, our idea will be to send all the artificial variables out, and then in the second phase we solve the problem without the artificial variables. Remember again, artificial variables were introduced because we wanted an initial basic feasible solution. So at the end of the two-phase method, when the artificial variables leave, then we will have a basic feasible solution without any artificial variable. From that point onwards, we can carry on with the simplex and solve. So let us explain the two-phase method again with the same example that we had. Now what we do in this two-phase method is, we have x1, x2, x3, x4, a1 and a2. We again start with a1 and a2. We have 2x1 plus 3x2 minus x3 plus a1 a2 equal to 8, and we have 5x1 plus 2x2 0x3 minus x4 0a1 1a2 equal to 12. Now what we are going to do now is, we are going to change the objective function coefficients. In the first phase of the two-phase method, we are now going to separate the problem to artificial variables and other variables. So all the artificial variables will have an objective function coefficient of 1 for a minimization problem, remember, for a minimization problem, and a -1 for maximization problem, and all other variables, decision variables and slack variables, uniformly will have a 0 contribution in the objective function. So now we start with a -1 here and a -1 here. Please remember that we are not using this 3x1 plus 4x2 in the first phase of the two-phase method. We are not doing that, we would put all zeros in this phase. Now we solve this problem again to try and get a basic feasible solution without the artificial variables. We do that like this. So we again write Cj minus Zj. Now this will be -2 minus 5, so you get a +7, you get a -3 minus 2, you get a 5, you have a 0, so a -1, 0 minus 1, you have a -1, you have a 0, you have a 0, and the value you have here is -20. Now variable x1 has the largest Cj minus Zj, so variable x1 enters. To find out the leaving variable, we again compute theta. 8 by 2 is 4, 12 by 5, so 12 by 5 leaves the basis. This is the pivot element. Now we have a1 and x1 -1 0, this is the pivot element. So, divide every element of the pivot row by the pivot element to get 1, 2 by 5, 0, minus 1 by 5, 0, 1 by 5, 12 by 5. We need a 0 here. So, this minus 2 times this row will give 0, 3 minus 2 into 2 by 5, 3 minus 4 by 5 is 11 by 5, minus 1, 0 minus 2 into minus 1 by 5 is plus 2 by 5, 1 minus 2 by 5, 8 minus 24 by 5 is 16 by 5. Now, Cj minus Zj values will be A1 and x1 will have A1 and x1 will have 0. Now, this will be minus 11 by 5 plus 0 is minus 11 by 5, 0 minus minus 11 by 5 is plus 11 by 5, minus 1 into minus 1 is plus 1. So, 0 minus 1 is minus 1, minus 1 into 2 by 5 is minus 2 by 5, 0. So, 0 minus 2 by 5 is minus 2 by 5. This is minus 1 into minus 2 by 5 is plus 2 by 5. So, minus 1 minus 2 by 5 is minus 7 by 5, and this will be minus 16 by 5. Now, this variable has a positive Cj minus Zj, it is the largest. So, variable x2 enters the basis. So, now I have to find out the leaving variable. 16 by 5 divided by 11 by 5 is 16 by 11, 12 by 5 divided by 2 by 5 is 6. So, this leaves, this is the pivot. Now, you have x2, x1. So, x2 has 0, x1 has 0. This is the pivot element. Divide every element of the pivot row by the pivot element. So, 0, 1, minus 5 by 11, 2 by 11, 5 by 11, minus 2 by 11, 16 by 11. You need a 0 here. So, this minus 2 by 5 times this minus 2 by 5 times this would give us a 0. So, 1 minus 2 by 5 into 0 is 1, 2 by 5 minus 2 by 5 into 1 is 0, 0 minus 2 by 5 into minus 5 by 11 is 2 by 11, minus 1 by 5 minus 2 by 5 into 2 by 11 minus 1 by 5 minus 4 by 55, that would give us minus 15 by 55, which is minus 3 by 11. 0 minus 2 by 5 into 5 by 11 is minus 2 by 11. 1 by 5 minus 2 by 5 into minus 2 by 11, 1 by 5 plus 4 by 55 would give us 15 by 55, which is 3 by 11. 12 by 5 minus 2 by 5 into 16 by 11. So, 12 by 5 minus 32 by 55, 132 minus 32 is 100. So, 100 by 55 would give us 12 by 11. So, Cj minus Zj values will be, this is all 0. So, you end up getting 0, 0, 0, 0, minus 1, 1 and 0. So, now the first phase of the two phase method is over. Now, let us go to the second phase. Now, at the end of the first phase, we now have a basic feasible solution with x2 equal to 16 by 11, x1 equal to 20 by 11. We do not look at the value of the objective function because we have changed the objective function. So, the purpose of the first phase is to give us a basic feasible solution without the artificial variables. Now from this solution we start the second phase, and the second phase goes like this. Now when we do the second phase, we leave out the artificial variables. We have only x1, x2, x3, x4 right hand side. For a maximization problem we would have minus 3x1, minus 4x2, 0 and 0. We now have a solution which is this: x2 with 0, 1, minus 5 by 11, 2 by 11, 16 by 11, x1 with 1, 0, 2 by 11, minus 3 by 11 and 20 by 11. The coefficients are minus 4 and minus 3 respectively. Now we compute the values of Cj minus Zj. The values will be x1 and x2 being basic would give us all zeros. We need to compute the Cj minus Zj only for x3 and x4. So this is minus 20 by 11 minus plus 20 by 11 minus 6 by 11 is plus 14 by 11. So 0 minus 14 by 11 is minus 14 by 11. Minus 8 by 11 plus 9 by 11 is plus 1 by 11. 0 minus 1 by 11 is minus 1 by 11. Minus 64 minus 60 is minus 124 by 11. Now it turns out that this is optimal because all the Cj minus Zj's are negative. So this within one iteration of the second phase we have got the optimal solution. If you go back and compare between the two phase method and the big M method, you will realize we are actually trying to do the same thing without introducing the big M. The reason why two phase method is also important is particularly when you start writing computer programs, there is always a question of how to define this big M. Now two phase method eliminates when you write a computer program you end up giving a large value for this big M, and one needs to be a little careful about those computations that come in the big M method. In some sense the two phase method does not have any big M appearing anywhere in the table, and it is a very logical method of solving it because the first phase eliminates the artificial variables. It tries to give you a basic feasible solution without the artificial variables, and then in the second phase you start with that solution. Now go back and bring the problem objective values and then check whether the remaining thing is optimal. So one could use either the big M method or the two phase method to solve a minimization problem, more importantly problems that involve these type of constraints. It is not the objective that matters, because we know that if the problem is maximization we keep the objective function as it is, if the problem is minimization we multiply the objective function with a minus 1. Therefore it does not matter to us. What is important or what is of concern is whenever we have this greater than or equal to constraint, for a strictly positive right hand side value the slack variable does not provide a starting basis. Therefore we need to introduce the artificial variable, and the moment we introduce the artificial variable we need to use either the two phase method or the big M method to solve. So let us look at this thing again. We show the same thing to you, the second phase of the two phase method which gives the optimal solution in this case. Next slide. Right, now this is something to do with initialization. There are a few other issues that are there with initialization. Now what are those issues? One, when do we introduce an artificial variable? So right now we said that if the problem has a greater than or equal to constraint and a positive value of the right hand side, then it would result in a negative slack or a surplus variable. Now we also realize somewhere that this artificial variable is an additional burden that we are imposing into the problem. The artificial variables do not exist in the problem. We introduce them simply because we want an initial basic feasible solution to start the simplex. Remember, simplex as an algorithm does three things. One, it always starts with a basic feasible solution. It iterates, it does not evaluate any infeasible solution in between, it continues to evaluate only basic feasible solutions, and it terminates. And because we are not able to get that basic feasible solution here, we introduce the artificial variable. We introduced the artificial variables, we added as many variables as the number of constraints in this example, we increased the number of problem variables, and then we also introduced a big M, and then we tried to eliminate the artificial variable and the big M. So obviously a good simplex implementation should have minimum artificial variables. It is not that we end up introducing an artificial variable for every greater than or equal to constraint. Now, there are situations where you do not really have to introduce an artificial variable. We do not have to introduce it for the sake of introducing it, we actually need to minimize it. So, these are the other aspects of initialization that we will see in the next lecture.